Hi everyone, welcome to our talk. My name is Tao Yan. This is my co-speaker Ken. Today we are very glad to be here to share our research about using code patterns to find bug variants and exploitation primitives in binaries with the help of our new pattern search tool. You can see our title is a SQL statement. Actually, it's a valid SQL query which can be processed by our new pattern search tool, and you can use it to find code patterns like whatever you want. We are security researchers from Palo Alto Networks. We are vulnerability researchers, Ponto winner, conference speakers in the meantime, and we are regular pattern inventors for new defense and detection techniques. Here's the agenda. Firstly, we'll cover background challenges, why we need code pattern search, and why we need a new code pattern search tool for binaries. Second, we'll cover everything about a new pattern search tool for binaries. And then we'll introduce how we create and search for unique code patterns in Windows binaries with our tool and find vulnerability variants and exploitation primitives. Last, summary and takeaways. Why we need static code analysis? On one hand, developers made similar mistakes repeatedly. For example, there are a huge number of memory copies, string copy vulnerabilities. Most of them are caused by not carefully checking the copy length. Besides, there are some bad APIs, such as smprintf, will return unexpected lengths, which will be misunderstood or misused by developers. On the other hand, similar vulnerable codes appear everywhere, but might possibly be patched in one place. So in those situations, static code analysis is a way to locate possible vulnerable codes. If we can categorize similar vulnerabilities and extract code patterns, code pattern search is a good method for vulnerability variance discovery. However, code pattern extraction is not always easy. Too complicated or too simple are both not good. Besides, there's no code pattern search to efficiently search code pattern in huge amounts of binary modules. CodeQL is awesome, but it's only for open source code software. In our presentation, we'll introduce our research and practices to solve those challenges. Then we'll come to the first part, a new pattern search tool for binaries. I will hand it over to my co-speaker, Ken.
All right. Before we get to the juicy part, I will do a brief intro on Leviathan, the tool that we built ourselves, because back then, to the best of our knowledge, there's no off-the-shelf solutions that could do binary code pattern search in binaries. We also decided to build our own query language because to facilitate the research and then automate away the repeatable task. Either batch mode works just fine, but it does get quite annoying at times when we have to constantly modify the scripts and run them against thousands of binaries. The tool was built on either Python hextrace API. The dependency on C-tree traversal makes the tool format agnostic and generic. Mark you, it is not a full-blown tool because it's primarily driven by our research. It should be sufficient for hunting bug variants and call patterns that have security implications. Some tweaking is likely needed, though, for generic reverse engineering. Here's a list of features that are currently supported. The search primitives are not only capable of finding variants and functions for our interests, but also call patterns like integer flow, expression in loops, and conditional checks. In addition, inter and intra-binary cross-references are also supported. And of course, tag analysis is like a must-have nowadays. This is how our tool looks like on the high level. Leviathan is the top layer that handles user interaction, as well as parsing, queries, and dispatching jobs. Handler is the second layer that interacts with our Leviathan library to carry out the work. The third layer, Leviathan util, is our library that provides abstraction to IDAPRO's APIs and structures for our handlers. You may notice that the inputs from query mode and script mode, they have different routes in the first two layers. But eventually, they'll tap into this layer to get a job done. At last, all the heavy lifting is done by IDAPRO and the hextrace decompiler. In addition to aforementioned code bases, we have 3 databases: command database is used to enqueue jobs. It's from this database that our handler will fetch the command query based on the command hash and does the work. Analysis result, as you may have guessed, is used to store the result. The result of each job is stored as a table. This allows quicker lookup if the query hasn't already been executed before. WinBin info contains workspace that stores the basic information of the binaries as well as that the user wishes to query. So what is a workspace exactly? In our terms, essentially is a database table that contains all the basic info of all binaries in a specified directory. This basic info includes function names, imports, and etc. A workspace is created via an init command when the user wishes to work on a set of binaries. In addition to info extraction, there are some simple heuristics that kick in and categorize the binaries. For example, system services likely have specific permission-related imports, like impersonation and reverse self. Services like RPC interface typically have higher privileges, so it's also worthwhile extracting this info. We did so by leveraging the IDA plugin called FindRPC. The categorization can speed up the subsequent search process because the user may only be interested in the subset of binaries that share similar features and functionalities. Here's a list of commands that Leviathan currently supports. Init, initialize a workspace. Set workspace is like switching to an existing workspace. Show workspace pretty much shows the current info of the workspace. Query enters the prompt for the command query. And create an exit. That's pretty self-explanatory. This is a diagram that shows what happens underneath when the user initializes a workspace. The main handler first creates an empty workspace or empty table. It then invokes the init handler to process all the binaries in the directory, extract all the relevant info, and store them in the workspace. This is the workflow when the user enters a query command at the prompt. When the main handler receives and processes a query, it fetches the target list of binaries from the workspace per the target filter, and then enqueues the command query. When the handler is invoked against the binaries, it first fetches the command query, does the job, and saves the result. Finally, the main handler fetches and displays the result. There are two search modes that the user can initiate at the query prompt. The first one is the SQL query mode. Just like any typical SQL query, it's designed to find a result in one or multiple SQL statements. And then there's a script mode. It offers more control on the granular level, since it's a combo of Python script plus our custom query syntax and APIs, which we'll get to in a second. Unlike query mode that only has partial access to all of Leviathan's capabilities, script mode has full access, and thus it can yield results with better accuracy. The query parser is based on SQL Parse, a Python package for parsing SQL queries. Since we have our own syntax implementation, it's nowhere near any of the real SQL query parsers used in real databases. While this mode only has access to a subset of capabilities that we provide in Leviathan, it's still enough to handle common tasks like conditional checks on functions' arguments, as well as flow analysis within the function. As shown in our design and diagram architecture slide, every dispatch SQL query command is handled by a generic handler, the IDA handler. This is what the query format looks like. Output filter is the selected output that the user wishes to display. Target is the binaries in the target workspace. It can be a subset of binaries, depending on the qualifier. This is where the binary categorization comes in handy, as the user may choose elevated service as target, for example. Finally, we have our own constraints like keywords and operators to narrow down our search. Here are some examples that we actually use for bug hunting. The first one is looking for target function with specific argument and type. The second one is searching for target function in all binaries in the current workspace. The last one is looking for functions containing the target function call in your target binary. If such functions are found, do flow analysis from the second argument of source function to the third argument of sink function. In order to get our backend and handlers to work with the user-supply SQL queries, these queries first have to be parsed and transformed into a format that both the handlers and the backend can understand, which is a Python dictionary. And this is exactly what a query parser does. As you can see here, the conditions and the corresponding key value pairs are color-coded in the same color to give you a better visual on the mapping. Once the query is parsed and stored in the queue, it's then fetched by the IDA handler, as shown in this snippet. The handler extracts the desired key value pairs and passes the value to the appropriate API based on the keys. In this example, the query command is looking for functions containing calls to import function, low library EX, with specific arguments. Thus, the handler first initializes import caller tracer, and then sets the anchor condition before it finally searches for the match functions. The reason why we chose Python dictionary because it meets these two criteria. First, it can nicely represent the parsed user input. Second, it works well with the condition-backed lookup and value comparison in a structured manner. Since it's straightforward to convert a dictionary to JSON and vice versa, it does provide some degree of flexibility for future changes, if any. And of course, this design is not final. We'll go with flow whenever and adjust however we see fit. As mentioned earlier, SQL query mode only has partial access to the search primitives. It is not by design. It's simply because it's hard to abstract certain patterns nicely in SQL format. As you can see it here in this one, the format can get quite convoluted. It's technically doable, but it's not very user-friendly. In addition, not all features are worthwhile incorporating them into SQL query mode. And that's why we resort to a script mode. The plugin used in script mode is a specialized version of our generic query handler, totally customizable by the user. Within this plugin, the user can leverage all search primitives and API to find call patterns of their interest. This is what the format looks like, pretty similar to the SQL query format. The only difference is the keyword pattern. This is how the handler knows which mode it should operate in. And this is how a script mode plugin may look like. In this example, the query invokes a plugin called int overflow, which searches for integer overflow expressions. Here, cfunc traverser is the key API that's used to traverse the C trees and control flow graph. The setConstraint functions is a function that allows us to do flow intent analysis. By passing the first argument, constraints, we effectively define the scope. The second argument is optional, and it's expression pattern that represents the code pattern that the traverser should look out for while it traverses the tree. In this case, it's looking for integer overflow expression pattern. The third argument is also optional. It's used for specifying 10 sanitizer. We implement our 10 sanitizer this way because there's just so many ways to skin the cat. So this is our utility and search primitives provided by Leviathan. Basic utility APIs are essentially just the wrappers that wrap around the IDA Pro's APIs for our need. Import caller tracer is the helper that performs function matching, as well as comment caller tracing. Conditional checks on the arguments and value are actually done by cfunc traverser. Cfunc traverser is the soul of Leviathan. It provides APIs and that users can use to do function matching, call pattern search, as well as intent analysis. So this is the format example for function matching. We have seen this before when we were talking about query mode and how it works. And this is how it works underneath. For condition 1, the traverser first finds the call C item and then checks for the function name. If the function is indeed a match, it then proceeds to check the subsequent conditions. Condition 2 and 3 applies to argument 1's value and type. So the traverser traverses to argument 1's corresponding C item, extract its type and value, and does the check against the target values. Condition 4 requires checking argument 3's value along with a bit mask. So this time, the traverser extracts argument 3's value, apply the bit mask, and does the check. Our expression matching format, on the other hand, is quite different, since its intended usage is for specifying expression as well as sanitization. Here's an example of real values. The outer condition is like an anchor, and the CE item matching the anchor condition is like a current pointer. As all the nested conditions won't be checked unless the anchor conditions are met. Next is like a next pointer. It instructs where the cfunc traverser should move the anchor to. This is important because our expression pattern matching is relative, not absolute. And this is how it works underneath. The conditions and the corresponding key value pairs are, again, color-coded in the same color to give you a better visualization. The dash pink arrows indicate the places that the anchor was previously pointing to. Yeah. The solid pink arrow means this is where the anchor is currently pointing at. Note that every condition is relative to where the current anchor is. As the traverser travels down the tree, all conditions must be evaluated to be true. Otherwise, you'll just stop and quit. And thus, the expression matching is not considered a matched. Flow constraint is used to set boundaries for our flow intent analysis. Boundaries are defined by all paths from the source to the sink. Each basic block in the path contains a list of C item indices, each of which are ordered by pseudocode line numbers. And our SC traversal is done in that order. Additional expression matching and sanitization can be applied during the process. Essentially, it's just like a dictionary of dictionaries in the code. Python has this awesome feature that allows one to add attributes to objects at runtime. And this is exactly how I do my tenting, by adding a tented attribute to every C item. As soon as the source is set in set constraint, the tent starts to propagate per the conventional propagation rules. During the propagation process, the variables are, of course, tracked, so we know whether the variable of our interest at a specific line is tented or not. Leviathan also supports cross-binary cross-references. It is done by our cross-ref handler, which basically leverages all the APIs that we have just described. In this example, the handler first finds the call path to export from the cross-flow sink from the previous job. It then tries to find the callers that involve these export functions in this current job. Finally, it enumerates the call path of all callers and search for cross-flow source. And that's how you build a relationship from the source to the sink. Now that we have some high-level understanding about the tool's capabilities, I will hand it back over to Tao, and he will show you how this tool is used in real bug hunting.
Thank you, Kim. After we know all details about our new pattern search tool for binaries, let's see how we use it to search unique patterns and find vulnerability variants and exploitation primitives. We will introduce 4 unique code patterns covering memory corruption vulnerability, logic vulnerability, and exploitation primitives. Let's start from the simple but classical file hijacking vulnerabilities. You can see there are 2 seed vulnerabilities. The first is the classical DL hijacking vulnerability. You can see the vulnerable function called load library to load a non-existing DL. So if the attacker create a fake DL in a directory from the past environmental variable, and when the vulnerable function is called, the fake DL will be load successfully. The second one is driver installer file hijacking, and you can see this file path can be fully controlled by the standard user, so the standard user can modify, override, or create a fake helloface.if and lead to some unexpected situations. It's straightforward to abstract the vulnerability model for the file hijacking pattern. You can see, firstly, create a fake file, trigger the file access, And a high privilege application access the missing file and load or open the fake file, which will lead to privilege escalation, whitelist bypass, etc. Based on that, we can extract the classical DL hijacking vulnerability pattern. You can see we will firstly search sensitive API calls such as load library EX, and query optional delay loaded API, which is less recognized but can also lead to DL hijacking vulnerabilities. And we also want to make sure the DL file is a constant string, not ends with a .dl, not start with API dash, not loaded as data or resource, and most importantly, not existing in a system directory. With that, we can create code queries for those three sensitive APIs. You can see our queries search the function contain the sensitive APIs and check the argument type value, and at last we'll check if the DL file is not existing in the system directory. Running those queries, we got those kind of results: load library 64, load library EX 521, and the query optional delay load API. We'll find 5 results. Pay attention to the last one, which is very interesting. It is related to Hyper-V host compute service and named Memcpy, and the vulnerable function actually call the query optional delay loaded API to load a CCG launchpad.dl, which cannot be found in the system directories. To find the triage, we traverse all call paths statically and find an interesting call stack. The vulnerable function is finally called by the service main, which means when the service started or restarted, and the vulnerable function will be called. And we can create a fake file in the directory from the past environmental variable, such as say Python, and when the admin start or restart the Memcpy service or fake CCG launchpad.dl will be loading into the process successfully. Second, reparse point pattern. You can see there are 2 parts in the state of vulnerability. The first part is read reparse point data. It calls device-level control with the device-level control code get a reparse point to get a reparse point data, and you can see there are some filtering by comparing the reparse point tags. After that, in the function in the right figure is used to process reparse point data, and you can see this line of the code which has the integer flow. There's a word value at a constant assigned to a word value. When the integer flow happens, this check will be bypassed, and the memory copy will cause out-of-boundary access vulnerabilities. And we extract the vulnerability model for this pattern like this: set a reparse point data, trigger reparse point data access, high privilege applications, get a reparse point data. Finally, the low privilege user controllable data will return to the high privilege applications. There are 2 parts in it. Firstly, comparing or filtering according to the reparse point tags, and then process reparse point data. Based on the vulnerability model, we extract the vulnerability pattern like this. You can see there are 2 steps. The first step is to find the reparse point read. To do that, we will search the device-level control function and check the second argument to see if it is a get a reparse point, and we'll search the code of comparing the output buffer with the reparse point tags. In the second step, we want to find the integer flow exactly. To do that, we will do tending from the output buffer to the memory copy, and we will check if there are word value plus a constant and assign the sum to a word value, which lead to the integer flow, and we will also make sure there's no integer flow check. With that, we can create the queries in query mode to find the reparse point read. You can see the query will search device control and check the second argument value, and also check the fifth argument to see if there's an equal or not equal to a number of constant lists. Here are examples of the WCI-related reparse point tags. After running the query, we can get some results. The functions which find the reparse point read. And if you want to step further to find the reparse point data process, and you can create a queries like this. Search the function which contain the reparse point read function, and do the tinting from the output buffer to the memory copy. Finding reparse point read and reparse point data process is good enough for us to get some result to review to find the possible vulnerabilities. But if you want to accurately find the integer flow, we can also implement in the script mode. You can see there are 4 steps in the script mode. The first step is to find the reparse point read, which share the same logic with the query mode. It uses import color tracer class to find the target anchor function, device control, and use cfunc traversal class to find the reparse point tag comparison. After that, in the second step, we'll find all the colors of the reparse point read function. And in the third step, we'll find the integer flow in all the colors with our customized expression matching mechanism. Here is a detail of the expression matching mechanism. You can see the first expression is to search and match this line of the code which has the integer flow, and you can see we will search assign operator, and we will check if there are arithmetic operation and a number pointer. And also we have the sanitizer expression to find if there's an integer flow length check. Running those scripts and queries, we got 5 results, and some of them got CVEs, and some of them were silently patched by Microsoft. And worth mentioning, we have one more results which is still vulnerable, so we have to hide details about it. And we can confirm all the results has a vulnerable integer flow and out-of-boundary access vulnerabilities in different binaries. Here's another example to find the triage. RPC interface function is one kind of entry point. We finally find the connection between the vulnerable function with the RPC interface function statically. And so we can create the RPC interface function in the RPC client and set a reparse point data in the meantime to crash the app info service. Third pattern, ACL, or overwritten pattern. The seed vulnerability for this pattern is very interesting, which we used in the Pontoon 2021. And you can see the vulnerable code will call getName secret info to get the ACL of a file with error-info in the ACL and calculate the ACL and set the new ACL to the same file by calling setName secret info. So if the attacker can redirect the file to a system file in this time frame, and the system file's ACL will be overwritten with error-info. Very interesting vulnerability. And you can see this is how we abstract the vulnerability model. Firstly, getName secret info call to get the ACL of the file with error-info. And when the setName secret info is called, the file is redirected to the system file. And after the setName secret info execution, the system file's ACL will be overwritten, which can lead to the privilege escalation directly. Based on that, we can extract the vulnerability pattern. It's easy to understand. Find the get name secret info, send name secret info, and check the second argument to see if it is file object, and find a common caller directly and indirectly. With that, we create the queries inquiry mode to search this pattern, and you can see the query will search function containing get name secret info, send name secret info, and it checks the argument 2 and set the trace indirect flag. Execution, the queries, we got a 32 result out of 637 elevated service binaries, but we cannot disclose it right now since they are still not patched. Actually, we have to blur several slides in this section, unfortunately, since we were asked to hide all details by Microsoft. It's a big pity, but we guarantee we'll publish all slides after they are fully patched in January next year. Vulnerability confirmation, pattern result, triage, demo. Last words for this pattern. This is very interesting. Zero-day story. The initial finding did not meet the Microsoft criteria, but based on that, we found a new attacking vector and reported 5 new vulnerabilities. Microsoft confirmed them, grant bug bounty to us, but when we request for vulnerability disclosure at Black Hat, we were asked to hide all the details until January 2023 because they are fixing the design issues. Very interesting, right? The last pattern, a pull spree pattern. Code patterns not work only for the vulnerability variance discovery, but also work for the exploitation primitives. Kernel pull spree is very important to the exploitation. In this case, we want to figure out how RDP client send what kind of PDUs to the RDP server for the kernel pull spree. Here is how we abstract the kernel pool primitive model. You can see the RDP client send one PDU containing many fields or many PDUs with client controllable data to the RDP server. RDP server receive and process RDP PDU and allocate many kernel pools and do the data copy to the just allocated kernel pools. Based on that, we extract the pull spree primitive pattern. You can see there are 2 steps. The first step is to find the data copy. To do that, we will firstly search kernel pool application and then find the memory copy to the just allocated kernel pool. There are 2 ways for that purpose: memory copy API and memory write in a loop. Besides, we also need to figure out which PDU can lead to the data copy. For this purpose, we have X-reference handler to find the call path from the RDP PDU data processing function to the data copy function. Firstly, we found the MCS ICE raw input as RDP PDU data processing function, but it contains the virtual function call in the call stack, which lead to the failure of the static function X-reference search. So we change Xflow source to the MCS and data callback function as RDP PDU data processing function. With that, we can create a queries in query mode to find data copy with memory copy. You can see the query search the function containing allocate pool with tag and memory copy, and we do tending. We will find if there's a data flow from the return address of allocated pool is tagged to the destination address of the memory copy, and we found several results in term.dd module, and you can see ICA channel input internal function is exactly what we want. And then we'll connect RDP PDU to data copy with memory copy. Like we mentioned before, we have X-reference handler to find the call path between the RDP PDU data processing function and the data copy function we just found. And we have found 2 results according the call stack of the first results. You can see there's a interesting function named invalidate rect. According to the function name, we found a specific PDU named refresh rect PDU, which can do the pull spray. Similarly, from the call stack of the second results, we have interesting function. I say channel import EX, and we finally found a PDU named client name request PDU in the virtual file system. So it saves us a lot of time to traverse 1,000 pages of the RDP documents. We mentioned before there's another way to do the data copy, memory write in loop. And you can see this expression is to search the memory write, this kind of memory write and in a loop. And we finally found 2 results in RDPWD module, and you can see handle persistent cache list function is exactly what we want. And after that, we connect RDP PDU data, RDP PDU to data copy with a memory write in loop. And similarly, we found the call stack, and according to the function name handle persistent cache list, we found a specific PDU named persistent K list PDU, which can be used to do the kernel pull spray. Finally, we created 3 different ways for the pull spray with RDP PDU, which can be used in the well-known RDP vulnerability bluekeep, and they are totally different with publish methods. You can refer more details in our Blue Hat talk. Last, summary and takeaways. Firstly, with the help of Hexray APIs, it's definitely viable to create a code pattern search tool for binaries. The idea of code pattern search primitives can also be used in other static analysis tools such as Binja, Ghidra. Second, we prove code pattern search not only work for memory corruption vulnerabilities, but it can also be used to find logic bugs which can not easily be found by fuzzing or manually code review, and also can be used to find new, less recognized attacking surface and new exploitation primitives. Third, in each case, we disclose the entire process of how to use code patterns to automatically find vulnerabilities and exploitation primitives in Windows with our tool. Hope you can get some inspirations from our detailed disclosures. Last words we want to mention. There's no silver bullet for bug hunting. Although you have the powerful tool to facilitate your research, deeply understanding your target is still the most important thing. Here is some links and references. And now we take questions. Thank you for listening.